Welcome to This Explainer. Today, we're jumping straight into a hidden crisis that is literally built into the foundations of our modern world. When you look up at those towering downtown skyscrapers or cruise down massive expressways, it's super easy to just assume the materials holding it all together are infinite. But spoiler alert, they aren't. We're actually facing a silent, massive shortage of modern civilization's most basic ingredient. We're talking about concrete. More specifically, we're going to explore a huge, vital shift happening right beneath our feet, the absolute necessity of swapping out natural river sand for artificial manufactured sand. Are we running out of the world's most basic building block? Well, for generations, the global construction industry basically relied on natural sand. It was the absolute go-to fine aggregate. But think about the sheer scale of global urbanization happening right now. Millions of people are moving into cities every single week. With mega infrastructure projects in Asia and massive housing developments popping up everywhere, the demand is just off the charts. Because of this explosion, natural sand is depleting fast. Actually, after water, sand is the single most consumed natural resource on Earth. Crazy, right? And because it's getting so scarce, it's getting way more expensive. But cost and scarcity aren't the only headaches here. It turns out, nature doesn't always deliver the perfect building material. Let's look at the hidden flaws of natural river sand, things like decayed vegetable matter, humus, moss and algae, and salt from tidal rivers. Natural sand is usually dredged up from dry riverbeds or coastlines, and it brings along a ton of hidden impurities. When rivers run low, a whole host of organic stowaways just settle right into the sandbeds. We're talking decayed vegetable matter, humus, the whole shebang. Plus, if you source that sand near a tidal river or the ocean, it's packed with salt, and salt is notorious in construction. It messes with the cement setting properties and causes that ugly efflorescence, those chalky white salt stains bleeding out of brick walls. These organic impurities aren't just a bit gross, they actively sabotage how the cement sets and bonds. So the equation is simple but dangerous. Moss and algae equals trapped air, which ultimately equals reduced concrete strength. These biological contaminants don't just hang out harmlessly, they actively weaken structures from the inside out. When moss or algae from natural sand gets mixed into wet concrete, it triggers a massive structural issue. They actually entrain or trap random unwanted air bubbles right into the mix. Now sure, sometimes structural engineers intentionally trap air for specific weatherproofing, but this uncontrolled, chaotic air trapping from algae, it's incredibly risky. It severely drops the structural strength of the hardened concrete, essentially creating microscopic weak points scattered throughout a building's foundation. It means a structure might not even be able to hold the loads it was mathematically designed for. Here's a quick definition of workability. It's the ability of aggregate particles to act like ball bearings and move past one another with ease during mixing and placing. Despite all the natural flaws we just talked about, the industry clung to natural sand for a long time for this one massive reason. In concrete technology, workability is absolutely everything. It's how easily wet concrete can be mixed, transported, and packed into molds without separating. Because natural sand has been tumbled by rushing water for thousands of years, the grains are beautifully rounded and smooth. In a wet mix, they act exactly like tiny ball bearings. They let the larger stones and cement paste just slide past each other, making the concrete super smooth to pour and easy to compact. Let's compare these sand shapes. On one hand, you have natural sand with its cubical, rounded shape, smooth texture, and great workability. On the other hand, early crushed sand was flaky, badly graded, rough, and produced incredibly harsh concrete. As natural sand started drying up, the industry scrambled to pivot to crushed stone sand. But honestly, those early attempts were a total disaster. Older crushing machines basically just smashed large rocks into flaky, elongated shards with jagged edges. And when you mix concrete with flaky sand, you completely lose that magical ball-bearing effect. Instead of sliding smoothly, those jagged pieces lock together. Engineers call this a harsh mix. It's stiff, notoriously brutal to pour, a total nightmare for workers to compact, and just awful for a fast-paced site. Thankfully, modern crushers produce cubical, smooth-textured, well-graded artificial sand. Technology finally caught up and completely changed the game. Those old, crude, rock-smashing methods got replaced by highly advanced crushing machines, specifically tuned for top-tier concrete aggregate. Instead of just blindly breaking rock, these modern marvels carefully shape the particles during the crush. They churn out manufactured sand that is perfectly cubical, really smooth, and exceptionally well-graded from fine to coarse. Thanks to modern engineering, we can finally produce an artificial sand that perfectly mimics, and honestly, in some crucial ways, actually outperforms the precise physical geometry of the best natural river sand. 15%. Manufacturing our own sand gives us a real superpower. Meticulous control over elements that nature completely leaves up to chance. And a huge one is dust. Dust is public enemy number one in fine aggregates. It acts like a microscopic sponge, soaking up all the water and completely wrecking the delicate chemical balance and workability of the mix. But with modern artificial sand production, automated systems rigorously seal and control the dust. The strict standard is that the maximum permissible fine dust, we're talking particles finer than 75 microns, must strictly stay at or below 15%. By locking this down in a highly controlled factory environment, we guarantee a drastically cleaner, more reliable foundational ingredient. Measuring the slump and flow of mixed concrete is absolutely vital. To really grasp how these engineering leaps play out on a real-world demanding construction site, we have to talk about slump. Slump is a highly practical visual test of how well freshly mixed concrete flows straight out of the truck. Hitting that targeted slump means your concrete is perfectly workable. It means you can safely pump it hundreds of feet straight up into the air, pour it seamlessly through thick webs of rebar, and pack it tightly without leaving dangerous empty voids inside the pillars. Simply put, if your sand is the wrong shape, or if it's way too dusty, your slump is off. And if your slump is wrong, the concrete is eventually going to fail. Let's dive into a case study using M60 concrete for a Mumbai high-rise. This real-world scenario absolutely nails why this shift to artificial sand is so critical. Over in the western suburbs of Mumbai, a massive high-rise project was underway. The structural engineers called for a highly demanding, exceptionally strong grade of concrete known as M60. Now, when you're building a towering skyscraper at this scale, you have exactly zero margin for error. The concrete had to hit super strict compressive strength numbers, sure, but it also had to maintain a very specific slump so it could be pumped hundreds of feet up without clogging the pipes or drying out too fast. Looking at the Mumbai high-rise results, natural sand completely failed to achieve the required slump, while manufactured sand achieved a highly workable mix with minimized voids. When they went to mix the concrete for this critical phase, the contractors initially tried using traditional natural river sand. But under the incredibly strict parameters of an M60 mix, the natural sand flat out failed. It was too unpredictable and it just wouldn't flow. So they swapped it out for precisely manufactured artificial sand. Because the sand had the exact engineered shape, perfect texture, and ideal mathematical grading, it minimized the void content flawlessly. The result? A beautifully workable concrete mix that effortlessly hit the exact engineering targets the natural sand couldn't even touch. What other natural materials will we soon need to engineer to save our environment and build our cities? It's a pretty profound realization, honestly. The sand we engineer today inside a machine can now reliably outperform the sand shaped by thousands of years of rushing rivers. By taking total control of the shape, the texture, and the chemical purity of our aggregates, we're making our buildings way stronger and our construction much more sustainable. So let's leave off on this thought. As natural sand inevitably runs out worldwide, and our engineering just keeps getting better, what other foundational elements of our world are we going to have to transition from harvesting to manufacturing? Thanks for joining me on this explainer, and keep questioning the foundations of the world around you.